relation between signals or inputs R of s d by dt of a parabolic signal, d by dt of parabolic signal is a ramp signal, and d by dt of ramp signal is a step signal, and d by dt of step signal is impulse signal. So, this is the way, if you know the response for parabolic input, then you differentiate this, you will get response for ramp. If you know the ramp response, differentiate it, you will get step response. That way there exists a relation between all the four signals this way. So, d by dt and then you get impulse. If you know impulse response, then integrate it 0 to t impulse response dt, you get step. And if you know step signal response step function, then 0 to t dt is ramp. And if you know the ramp response, integrate it to get parabolic. So, this is the way, if you know the response, you can find out another response, maybe by differentiating or by integrating, depending on the function that is supplied to us. So, there are two important things in control systems. One is speed of response and the other one is stability. Stability is related to that when you have given some input, that output should be within the limits. For a bounded input, you should get bounded output. So, stability is one aspect, speed of response is another aspect. So, the time response analysis, we would like to see that a particular system described by its order, first order, second order and so on, that is excited by certain inputs, then what is its response? That response, how fast it is, how slow it is. So, we will have some information that we can say that it is a good system if the speed of response is very fast. If the response is faster, we say speed of response is good, so it is a good system. For that purpose, let us now see, for a first order system, we excite by some inputs and then what is its response. So, let us consider again the simple RC circuit. It was discussed many times in the previous classes, and voltage across the capacitor consider as V naught and input voltage is Vi. So, for this RC circuit, the transfer function, you can actually have V0 of s by Vi of s. In general, it is called as C of s by R of s is 1 by RCS plus 1, 1 by RCS plus 1. This same circuit, if you remember, we can represent it as a block diagram as C of s, R of s and then unity feedback control system, and here it is 1 by RCS. Now, this feedback is 1 and you can consider this as G. G of s is open loop transfer function given by 1 by RCS, means 1 by tau s. So, if the loop is not connected, then the transfer function of that particular system is C of s by R of s is simply G of s. That G of s is given by 1 by tau s. What it indicates? That means there is a pole at s is equal to 0. Now, when you close the switch, when you close the loop, then what will be the transfer function? It will be G of s by 1 plus G of s is equal to, G of s is 1 by RCS. So, if you do this G of s by 1 plus G of s, you get 1 by RCS plus 1. This is also written like 1 by tau s plus 1. What happens to the pole now? Pole at s is equal to minus 1 by tau, so it is not at 0. So, loop closed, not closed has some meaning. If the loop is not closed, pole is located at origin. The moment the loop is closed, the pole has been shifted to some location from here to here minus 1 by tau, means closed loop system making the system more stable, because pole is being shifted from origin, away from the origin towards left half of the S plane. So, we say that it is good if the loop is closed. Anyway, this is a first order system, 1 by RCS plus 1 or 1 by tau s plus 1. So, that is the response you got. C of s by R of s is equal to 1 by tau s plus 1. I say it is a first order system. Now, I want to have the time response, means C of t. So, when I say C of t, this C of s, you need to apply inverse Laplace to get C of t. Now, R of s is very important, that I need to consider this R of s as impulse, R of s as step, R of s as ramp, and then see what is C of s, then what is C of t. That is what we do in time response of first order system. So, let us consider first R of s is equal to 1 by s, means it is a step signal, unit step signal. For this, what is C of s? You get C of s is equal to R of s is 1 by s. So, take this side 1 by s into 1 by tau s plus 1. Now, this is C of s. So, I need to get C of t. So, I need to apply inverse Laplace transform, but before that you need to get partial fractions. So, by applying partial fractions, you get this as a by s plus b by tau s plus 1. So, you need to get a and b constants, and what you get here is a as 1, b as minus tau s plus 1. That means you have got a function now still in S domain. Now, you need to get from this C of s as C of t. 1 by s is 1 inverse Laplace transform minus, this can be little simplified as 1 by s minus 1 by s plus 1 by tau. I am just rearranging the term tau, and this tau is taken out, you have got 1 by s plus 1 by tau. So, now minus, what is the inverse Laplace of this particular term, the second term, e power minus t by tau. So, it is the general function C of t is the response with respect to time for first order system as 1 minus e power minus t by tau, means you can see now r of t is 1. R of t is 1 because Laplace transform of r of s is unit step is 1 by s. So, you get now c of t this way. You get c of t like this. Please remember that this exponential increase is because of the capacitor, and for that reason in the response you have two terms, 1 minus e power minus t by tau. The second part is transient part. So, that transient part is making the response to increase exponentially, and then finally it is reached steady state. So, 1 is the steady state and this exponential term is transient part. So, generally if you see that at t equal to tau, at t equal to 0 it is here, at t equal to tau you get 0.632 at t equal to tau, at t equal to tau you get 0.632. So, how much time the response takes to reach the steady state? Generally it is in terms of time constants. As you know, for RC circuit the time constant is RC. So, it takes 4 to 5 times tau for the response to reach steady state. That means in the steady state you can see here it takes about 5 time constants. It is taking 5 time constants time to reach the steady state response. This is about time response of first order system for unit step input, Next we will see the time response of same first order system, but not excited by unit step, but it is excited by unit impulse. In the previous section we have seen the response for step input. That step input is applied to the first order system. Now, let us see the response of the system of first order, but this is excited by now unit impulse. So, as you know anyway, the transfer function c of s by r of s is 1 by RCS plus 1, where time constant tau is 1 by RC. So, it is 1 by tau s plus 1. Now, R of s is 1 for unit impulse. R of s is the Laplace transform of unit impulse, it is equal to 1. So, C of s is no change actually, because R of s is equal to 1. So, it is just multiplied by 1 the function. So, you get as it is C of s or C of s by R of s is same. That is why the transfer function is also defined as impulse response, because impulse response is 1 by tau s plus 1, same as transfer function, because R of s is equal to 1. Remember, for stability we can also define this way, that the impulse response must decay as early as possible, then we say it is a stable system, because impulse is undesirable signal. If that signal come across any system, response due to that impulse input must die as early as possible for a good system. So, if you see that C of s is 1 by tau s plus 1, you can actually write this as 1 by tau by s plus 1 by tau. So, this is given by 1 by tau e power minus t by tau C of t. So, this is C of s and C of t is now 1 by tau into e power minus t by tau, where tau is the time constant of RC circuit. Now, if you see the response, impulse response C of t, that function is 1 by tau, means when t equal to 0, the magnitude of this signal is 1 by tau and this will decay as time approaches infinity. So, you are increasing the time because it is a time response of a first order system for impulse input. So, this is tau, 2 tau, 3 tau, 4 tau, and by the time is equal to 5 time constants, that impulse response has become 0. So, this is a stable system, I say, because time response is decaying as fast as possible. So, this is the time response C of t of first order system for unit impulse input. Now, let us see the time response again of first order system for unit ramp input. So, system is same again, no change in that, it is a first order system. But the input is changed now, this R of s is now unit ramp signal. So, I again write the transfer function C of s by R of s is 1 by tau s plus 1, first order system. Now, the R of s we need to consider as unit ramp. So, R of s is 1 by s square. As you know, ramp signal is represented by R of t, it is equal to t, unit ramp. This signal, as I just now explained, that it varies linearly, ramp function varies linearly and whose Laplace transform is 1 by s square. So, as usual, I want to get time response, means C of t. So, first I should get C of s, because R of s is equal to 1 by s square. So, you write now as 1 by tau s plus 1. So, expand this function into partial fractions, you get 1 by s square minus tau by s plus tau by tau s plus 1. So, you apply now inverse Laplace transform C of t. When you apply inverse Laplace transform, 1 by s square is t, 1 by s is 1 only, that means it is tau, plus tau into e power minus t by tau, the response. So, this is nothing but t minus tau into 1 plus e power minus t by tau. So, this is actual input. Please see again that ramp input that is given here, it is varying linearly. As you increase time, the signal function increases. So, this ramp input, now the response, finally this is steady state response. This is nothing but steady state response, and this part is transient part. So, when I say this is R of t, C of t will be like this. This is C of t. So, in the steady state, whatever error you have, this is called steady state error. So, the time response of first order system for unit ramp input follows this, and there is an error that is actually given by tau. Tau means the time constant of RC circuit. So, it should be as small as possible. Remember, it should be as small as possible so that the error is minimum, because our aim is to see that the response C of t must follow the input as early as possible without much error. So, this is the time response of a first order system for unit ramp input. Minus tau is taken out. Yeah, this will become minus. Now, let us see the response of second order system again for the various inputs. So, before getting into the time response for various inputs, I would like to see the second order system in terms of electrical components. As you are aware, for this second order system, now because there are two energy storage components, it becomes a second order system. So, as usual, when you apply KVL to this particular loop, assuming I in the circuit, Vi is equal to Ri plus L di by dt plus 1 by C integral I dt. This is one equation, and V0 is 1 by C integral I dt is the second equation. Now, this equation can be written as Vi of S equal to R into I of S plus Ls into I of S plus 1 by Cs into I of S. Whereas, when you apply Laplace transform to this, V0 of S equal to 1 by Cs into I of S. Now, I can rewrite this equation as I of S into R plus Ls, only first two components, and this third component 1 by Cs I of S is output voltage V naught of S. So, if I want to get now I of S, V I of S minus V0 of S by R plus Ls, R plus Ls. And if I want to get now V0 of S is equal to 1 by Cs into I of S. This I of S you can substitute Vi minus V0 by R plus Ls. So, this becomes 1 by Cs into 1 by R plus Ls into Vi of S minus V0 of S. I am interested in output voltage V0 of S. It is 1 by Lc by S into S plus R by L into Vi of S minus V0 of S. So, now let me draw a block diagram describing this particular equation. Vi of S is input, and this is a block 1 by Lc by S into S plus R by L is the block, and then you have V0 of S and a loop, because Vi of S minus V0 of S is the output of this error detector, and this block is multiplied by this error, you will get V0 of S. That is the way the block diagram is drawn, and this can be considered as G now, or G of S is equal to 1 by LC by S into S plus R by L. And if you see this, if I am interested in getting G of S by 1 plus G of S, because it is the closed loop transfer function, in general it is called as C of S by R of S, but in this case in electrical system it is nothing but V0 of S by Vi of S leads to 1 by LCS square plus RCS plus 1. This is the function actually you get. You can rewrite this as 1 by LC by S square plus S into R by L plus 1 by LC. So, in the next class what we see is, this is considered for an electrical system. So, this second order systems may exist even for a mechanical system, pneumatic system, thermal system. So, we should have some standard representation of second order system. So, we will consider in the next class the second order transfer function of standard order that can be useful for any type of system, maybe electrical or mechanical or thermal. So, using that we will try to analyze the performance of a system. So, we will discuss the standard second order transfer function in the next class.